In this lecture, we're going to look at different methods of hierarchical clustering. We're going to look at agglomerative clustering, which is a bottom-up algorithm that starts with all the examples divided into clusters of one example each, and then joins together those that are more similar and gradually does that until all the examples are joined together or until we reach a desired number of clusters. In divisive clustering, we approach the problem in the other direction, starting with a single cluster with all our examples and then dividing the cluster until we reach the desired number of clusters. In both cases, we are doing hierarchical clustering, which means that there is this notion of clusters belonging to a group of clusters and then groups of those groups belonging to larger groups and so on. We're also going to see how we can use agglomerative clustering, for example, for clustering features. This can be used for dimensionality reduction, and we have a handy class for this in scikit-learn. In theory, any kind of clustering algorithm could be used for this, and we also saw previously how we did a sort of reduction in the range of values that we had with k-min, so that could be another approach to dimensionality reduction, but we're going to see an example of that using hierarchical clustering. So what is hierarchical clustering? The idea is that we are creating groups that are grouped into larger groups and so on in a hierarchy of groups. One example of this would be the phylogenetic tree of life, where we have groups of animals, fungi, plants, and so on, and these belong to a large group, eukaryote. We have these archaea and bacteria, and inside these groups we can also find smaller groups. For example, in animals we have primates and other groups of mammals, reptiles, and so on. So we can think of hierarchical clustering as a structure where we are grouping things together and then grouping the groups again and so on. Another example of application of hierarchical clustering could be to find the relations between, for example, different organisms based on gene activity patterns. And again, we have this dendrogram, this tree-like representation, where we can represent all the smaller groups and how they are grouped together into larger groups in a hierarchical structure. So the idea here is that if we want to create this hierarchy of groups, for example, if we have this data set, these elements here, we could start by grouping together these two, B and C, because they are very close together. D and E are close together. And so we have this first layer of groups where we have B and C, D and E, and then we have F and A separated. But then when we step to the next level, we could consider that D, E, and F form one group because they are closer here. So at this level, we would have D, E, and F in one group, B, C in another group, and A at another group. And then we could go at a higher level where we would separate A from the other 5 elements. And so in this case, we would have 2 groups, one formed by A and the other by B, C, D, E, F. And then finally, when we go to the largest group here, it's just the set of all the examples that we have. So we can represent a hierarchical clustering with a dendrogram, a tree-like representation like this, where we can see the different levels of the hierarchy. What we need to do here is, just like in other cases of clustering, we need to be able to measure how alike or different the examples are. We saw that we have different ways of doing this. We can consider proximity as a generical term for how alike two things are. Similarity, usually similarity is in a range between 0 and 1, but it can be also taken to mean something more broad, more vague as proximity. Dissimilarity would be the opposite of this, so measuring the difference instead of the similarity. And there is a particular case of distance. Distance is a dissimilarity measure that fulfills these conditions. So it's 0 or more. There is no negative distance. It's symmetrical. The distance between point X and Y is the same as point Y and X. And it fulfills this triangular inequality. So the distance between x and z cannot be larger than the distance between x and y, and then y and z. So going through these two steps cannot take us a shorter distance than going straight from x to z. So if we have some measure of dissimilarity that fulfills this criteria, then it's a distance measure. But this is what we saw previously. Also, we always need some way of measuring how alike or how dissimilar or how distant our examples are in order to cluster them together. But with hierarchical clustering, we need more than this. So this is just some examples of distance measured. Just to review, we already saw that there are some cases here that are special cases of the general Minkowski distance. It depends on the order of the root and the power there. For example, Manhattan distance when we use 1 as the power and the root, Euclidean distance when we use 2, and so forth. But then there are other ways of measuring distance between examples. For instance, Mahalanobis distance is the normal Euclidean distance, which is this the difference between the two vectors transposed and multiplied by the vector in the other direction. So if you do this, you get the same as this expression here, but it's also divided by the covariance of these variables here. So basically, we are normalizing this by how spread out the values are. Hamming distance is used in strings, for example, text documents, sequences, things like that, which is basically the sum of the differences between the strings. Levenshtein distance is a bit more sophisticated. It tries to use the smaller number of mutations, so insertions, substitutions, deletions, and so on, that would have to happen to go from one string to the other. This is particularly relevant in biology, but there are many distances measures that can depend on different problems that we are looking at. But basically, this is the core of what we need for any clustering algorithm. We need to be able to measure some differences, likeness, or distances between examples. However, in hierarchical clustering, we also need to be able to compare clusters. So in this case, we talk about linkage, which is how we are going to determine if two clusters are close together or are apart in order to decide when to group them together. So just like we have with distances between examples, we can have different criteria for linkage between clusters. And we're going to see here some examples like single linkage, complete linkage, and so on. But the general problem here is how can we convert these distance matrices or apply these distance metrics that we are using to compare examples, but instead of comparing individual examples, we are comparing groups of examples. So one thing we can do in this case in single linkage is that we consider the distance between two clusters to be the smallest distance between any pair of points from one cluster to the other. So X belongs to cluster J, Y belongs to cluster K. We choose the X and Y points that have the smallest distance, and that distance will be the distance between the clusters. So given these two clusters, red and green, we measure the distance between them as the distance between the closest points here. So this is called single linkage and is a way of using the distance metric that we are using between our points and apply it to measure the distance between clusters. Complete linkage, we do the maximum instead of the minimum. So the distance between the two clusters is the distance between the 2 points, one from each cluster, that are furthest apart. So the maximum of the distances between all of these pairs of points. And this is another way of converting distance to between examples to distance between clusters. The centroid linkage is the distance between the average of the coordinates of each of the clusters. So basically, we compute the centroids of the two clusters and then the distance between these mean points in the clusters. More examples: average linkage, we take the average of the distances between all pairs of points from one cluster to the other. Median linkage, we take the median instead of the average. There is, for example, word linkage is not quite a measure of distance, but it's a loss function that we are trying to minimize. So basically, we are considering how to group together clusters or not, depending on how well they reduce this sum of the squared distances between all the points and the centroid of the cluster they belong to. So we can use this as a guide to decide whether or not to group together two clusters. So the idea here in hierarchical clustering is that in addition to some measure that we can use to compare examples like distance, similarity, and so on, we also need some measure that compares clusters. And this we call linkage, and it's a way of using distances between points or other metrics in order to compare the clusters. One advantage of hierarchical clustering is that we do not need to assume a particular number of clusters, because the hierarchy will give us several different levels at which we have different numbers of clusters. So we can just keep the algorithm going and then choose when to stop, or not stop and have the complete tree and then choose how to interpret that. Also, the hierarchical organization of the clusters may reflect some deeper structure in the data. For example, if we are comparing sequences of proteins from different organisms, we can get a phylogenetic tree that represents how the genes for those proteins have been evolving over time and how related they are. There are some disadvantages. The problem of computing all the possible trees for hierarchical clustering is exponential, so we cannot really do that exhaustively in practice. And basically, we need to have some heuristic methods that cut through all that search space and follow a straight line, so to speak, a single set of steps until we get our clustering. And if we make some incorrect decisions along the way, then the result may not be very good. Also, if the data itself is not hierarchically organized, then hierarchical clustering will not reflect a structure of the data and will just be some artifact of the way we cluster the examples. So it may not be applicable in all cases. Okay, so let's look at two different approaches to hierarchical clustering. In agglomerative clustering, we are clustering the examples from the bottom up. This means that we start with clusters formed by single examples. Each example is its own cluster. And now we're going to join the two closest clusters, or the two best to join by some linkage measure that we use, and we're going to repeat that until we join all the examples into a single cluster and we store the tree that we are getting along the way, or we can stop when we reach a desired number of clusters. So we can use agglomerative clustering, specifying how many clusters we want, and agglomerative clustering will keep joining together clusters and examples until we reach that target value. It's generally on the order, the complexity of this algorithm is on the order of the cube of the number of examples that we have. But if we add linkage constraints, which means that we do not consider all the pairs of examples when trying to bring together different clusters, then this can reduce the complexity and speed up the algorithm. A different approach is going from the top down. We start with all the examples in a single cluster, and now we find some way to split it into two clusters. We can do this with some algorithm that can split the examples into two clusters, and now we're going to repeat this. In theory, if we wanted to do an exhaustive search of all the possible splits, this would be on the complexity will be on the order of 2 raised to the number of examples that we have. This would explode exponentially, and so it will not be practical. But if we have some algorithm that we can use to split, and it's a fast algorithm, for example, k-means with k equals to 2, we can use that as a heuristic and not explore all the combinations, just follow what that algorithm is telling us. And it can be a good approach if we want only a few clusters. Note that if we only want a few clusters with agglomerative clustering, we have to cluster starting from all the examples in different clusters and then repeating this many times until we reach a small number of clusters. On the other hand, if we use a top-down approach of divisive clustering, we quickly reach a small number of clusters because we just need to do a few steps dividing the initial cluster. So let's see some examples. Agglomerative cluster, imagine that we have this data set. So our starting point is each example in our data set is its own cluster. Each cluster only has one example. And now we're going to find the examples that are closer together and merge them into clusters. And we are going to do that also using the linkage measure. We are going to do that for the clusters too. So we start by grouping together things that are very close, and then we start grouping together groups that are close, and so on, until we have all these connections made between all the groups. And this leads to a tree where we have the last connection that we made, the first connections that we made here, and we have all of these connections between the different groups. And we can find in this representation the hierarchy of groups. We have one group here, then we have 3 groups here, for example. We have all of these smaller groups down here below, and we can choose how to cut this tree into different clusters. So if we want a partitional clustering, all we need to do is select a level on the dendrogram to cut the tree. For instance, if we do it like this, we have 2 clusters, which is cutting on this connection here, and now we separate everything into 2 clusters. Or if we want, we can go further below, have 3 clusters or 4 clusters, and so on. So we can choose which branches of the tree to cut to separate into different clusters. Another thing that we can do with agglomerative clustering is to impose some constraints on how the linkage is done. So suppose that we are doing agglomerative clustering on this set of data in 3 dimensions, and we are stopping at a fixed number of clusters. So in this case, we have a blue cluster here, yellow, black, red, cyan, and green. So 6 clusters, we are getting 6 clusters here. But this is not a very good clustering, because you see that the black cluster includes points on this side of the ribbon and here. The blue cluster includes points here, and this is a bit strange in this way. So we not only because of performance issues, because this is generally on the order of the cube of the number of examples. So if we have large data sets, this can take very long to compute. But also we may not want to consider simply the distance, but we may want to ignore these jumps here over space and try to do the clusters more along the structure of the data. So one thing that we can do to achieve this is to add connectivity constraints to the agglomerative clustering. And the idea here is that we consider the linkage between examples and between groups in general only if the examples are connected between them. So whenever we are evaluating linkage between groups, we only do that if we can find examples between one group and the other that are joined in this connectivity structure. So this forces clustering to respect the structure of the data if we find a connectivity matrix that can represent this structure. So basically, a connectivity matrix is a matrix of n by n, where n is the number of examples that we have. We can use a sparse matrix. This is a compact representation that NumPy also can use, and scikit-learn uses that implementation, that you can use when you have a matrix that is mostly zeros and only a few non-zero values. So actually this matrix takes up a lot less space than n by n cells. And the idea is that this matrix has a value of 1 on all pairs that are connected. One way we can do this is to use this k-neighbors graph that you can get in the neighbors module of scikit-learn, and given a set of data points and the number of neighbors, it will give you a connectivity matrix that has a value 1 connecting all the pairs of points if they are among the n nearest neighbors of each other. So each point is basically in this case connected to 10 other points that are the 10 nearest neighbors. Everything else is not connected, so distant neighbors are not connected here. And then we can do the agglomerative clustering using this connectivity matrix. In this case, I'm using word linkage. You can use word linkage if you have an Euclidean distance measure. If you have different distance measures, then word will not work. But now I'm doing this with 6 clusters and using this matrix for the connectivity. And in this case, it's not only faster, because now we don't need to find to use all the pairs of points when computing the linkage between the clusters. We only need to look at the connected points. So each point is only connected to 10 neighbors. And the result is much better. So without constraints, we cluster together these parts of this ribbon because we are considering only the distance, and at some point clusters here get merged with clusters here. But if we impose that connectivity constraint, we get this result. These are the 6 clusters that we get along the ribbon, and you see that there is no jump here through space. This is because our connectivity constraint only connects each point to the 10 nearest neighbors, and they are always on the same part of the ribbon. So our connectivity matrix follows this structure of the data, and since linkage is only computed along the edges of that connectivity graph, then these clusters here will never get merged with these ones unless they get merged all the way along this ribbon. So using agglomerative clustering with scikit-learn, you can use this class, agglomerative clustering. You can specify the number of clusters. Note that agglomerative clustering is hierarchical, but we can use it as partitional clustering if we specify how many clusters we want to stop at. This is the affinity metric that we use. In this case, this is Euclidean distance. The linkage by default is word, but you can use different linkage. You can use different measures for distance, or you can use a function or a matrix and so on. This is just like with other clustering algorithms in scikit-learn. And basically, this does the hierarchical clustering, but then it stops when it reaches the number of clusters that we specify. We have not only the labels at this level, the partitional version here, but we can also find the children and the hierarchy here in the clustering. Different linkage measures will tend to give us different types of clusters. For example, complete linkage, when we use the largest distance between the clusters as a linkage measure, tends to favor larger clusters. Larger clusters tend to grab more space and grow more. Average linkage solves this problem a bit, so clusters do not try to grow that large. Word linkage tends to work better, but you can only use it with Euclidean distance measures. In any case, trying to minimize the sum of the quadratic distances between the points and the center of the cluster is generally what intuitively works better for clustering. Divisive clustering tackles this problem of hierarchical clustering going from the other direction. We start from the top with a single cluster for all the examples, and then we repeat this iteration by selecting one cluster, for example, the cluster that is largest or has the lowest score or something like that that we are using to measure the quality of the clusters, and then we split it. We can split it in the case of bisecting k-means, this algorithm. We are doing divisive clustering using k-means with k equals 2 to do the split. And now we can do this until we reach the desired number of clusters, or eventually we get the whole tree if we want. So to illustrate, we start with a single set of points, and then we split the cluster with k-means, and we keep doing that, selecting clusters. In this case, I'm selecting the clusters based on the number of examples, and then we keep splitting until everything is a single cluster. So this is the first split, the second, the third, the fourth, and so on. And now we can store all of these splits and build the tree corresponding to this hierarchical cluster. So this would be the first application of k-means, splitting into two parts. Then we have the second one here, the third one here, then the fourth, the fifth, and so on. And we are following through these iterations and breaking down our initial cluster into smaller and smaller subclusters. So we can do this and either obtain the complete tree. If we go all the way down to singleton clusters, to individual examples, we obtain the complete tree, but we can stop this at any level that we want. So if we want, for instance, 2 clusters, we can do just 1 step. 3 clusters, we do 2 steps and we get 3 clusters, and so on. If we want a small number of clusters, then probably divisive clustering is faster than agglomerative clustering, because for a small number of clusters, agglomerative clustering will have a lot more iterations than divisive clustering. If we want to do an exhaustive search on all the possible ways of splitting our data, this would be a combinatorial problem with an exponential complexity, so we don't do this in general. What we do is we use a clustering algorithm, for example, k-means, in this case of bisecting k-means, which is fast and allows us to do 1 step of splitting in half. And now we just need some criteria to select which cluster to break down next. So in this particular example, the criteria that I used was always to split the cluster with the largest number of examples. So I always chose the one with the largest number of examples. But we can use different criteria and just keep splitting the clusters. This may be a good option if we want a few large clusters. However, it may not be very good if we want everything, and if we have some problems with the auxiliary clustering algorithm that we are using to split the large clusters. Because if we make some mistake along this process, we can never fix it, and so these mistakes will accumulate. So divisive clustering, like agglomerative clustering that we saw, these are heuristic algorithms that do not explore a significant part of all the possible trees that we could have, because that would be a very large search space. And so the choice of these algorithms may also depend on which one works better for the kind of data that you have. Now, one thing that we can do with clustering is not only to cluster examples, but also to cluster features in order to reduce the dimensionality of the data that we have. Consider a general matrix that we have been using, where we have our data set, where each row corresponds to one example, and each column corresponds to a feature. And this is generally the way we store our data. Now, when we're using clustering, what we're doing is we're joining examples together into groups. But if we imagine that we transpose the feature, the matrix, exchanging the features and the examples, we would have a matrix where each feature is a row and we have the value of that feature for all the examples, and each example is a column, and so it's this column has the values of all the features of each particular example. But now if we feed this as a normal matrix into the clustering algorithm, it will interpret these rows as examples and cluster them together, and we'll be actually clustering features together. So this is something that we can do to reduce dimensionality in our data. Basically, we're going to cluster similar features together, and then we can create a new data set with a smaller set of features by aggregating the values that we have of the features that are closer together. For example, computing the average of the feature values in each group. Let's see an example to illustrate this. This is a classical data set, handwritten digits data set, where you have handwritten digits, in this case represented in grayscale images with 8 by 8 pixels. So we have 64 pixels in each image, and they are representing different digits written by hand, 0, 1, 2, and so on. We can reduce the number of features from 64 to 16 by converting this matrix of 1,797 examples. This is the number of digits that we have in our data set. And we can convert this into a matrix of this number of features and only 64 examples. So instead of having 1,700 examples with 64 features, we have 64 examples with nearly 1,800 features. And now we're going to cluster these 64 features, where each feature corresponds to a vector with the value of that feature for all the examples. And now we're going to cluster this into 16 clusters using the aggregating the more similar features. We're also going to do apply a constraint, a linkage constraint to our clustering, so that only adjacent pixels can be grouped together in the same clusters. So we're going to create this linkage constraint and use agglomerative cluster for this. So basically the idea is to take the original data, and now we're going to look, for example, at the top corner pixel of each image. We create a vector with the value of that pixel on all images, and then we use the same thing for the second pixel, the third, and so on, and we group together those that are more similar across all examples. We can do this with feature agglomeration, and this is this class here uses agglomerative clustering, but applied to features. So it automatically does this transposition of the matrix and allows us to do the transformation into the reduced representation of our data. So it's a class that is specifically designed for clustering features. And we can use this grid to graph auxiliary function here to create the connectivity graph in a grid. So basically, imagine that we have a grid that has this 8 by 8 dimension. So it's the shape of the images that we have. And we want to consider 2 points to be linked if they are neighbors in the grid. And now this creates this connectivity matrix, which will be a matrix of 64 by 64 with 1 on every pair of points that are neighbors in this grid, and 0 on the others. So when we use this connectivity restriction on agglomerative clustering, we force the clusters to be created by sets of contiguous pixels, so contiguous regions on the image. And now we can fit this to our data. Our data is just the set of images that we have, but each image containing 64 features. We are reshaping so that we have 1,797 rows and 64 columns. We fit to that data, and now we can reduce the dimensionality of the data, obtain a matrix with fewer columns, with only 16 columns, because this is what we specified here, by using the transform method in this object. So after fitting, after the clusters have been computed, the transform method averages all the features in each cluster and returns the reduced representation with fewer features, with only 16 features, by averaging those in the cluster. And now we can also do the inverse transform, which is going back from this reduced representation to the original one with 64 features, but now copying the values to these different pixels. Okay, so let's visualize the results. It's easier to understand if we look at this. So these are the 16 clusters that were created. If you look here at the images and consider this connectivity constraint that we added this connectivity constraint so that we could not have clusters of, say, one pixel here and then another pixel there and so on, just because they happen to be similar. So the taken all across the images, in fact, these corners, for example, the pixel here on this corner and on this corner is probably very similar because they are probably zero in nearly all images. But because of that connectivity constraint, we cannot put these two in the same cluster without putting everything in between in the same cluster. So we have one large cluster here, which corresponds to the 2 pixels here on the left side that tend to be mostly black. We also have a large cluster here on the right side that these pixels also tend to be very similar to one another. And then we have some clusters, smaller clusters here, because here the pixels vary a bit more. But these are the 16 clusters that we found. So now we can aggregate these pixels together and just compute the average value of these pixels across all the average value of these pixels for each image. So in one particular image, we would average all of these pixels, and this would just be one feature for that image. So from this original data, we can now represent this by averaging the pixels in the same cluster, and we have this simplified representation of the data. So all the pixels here have the same value, all the pixels there have the same value, and so on. We can do this for each image. But since we only have 16 clusters, we actually only have 16 different values. So we can represent each of our digits. Instead of using an 8 by 8 image, we can represent them, for example, in a 4 by 4 image. So as you can see here, we no longer see the actual digits because this is a compressed representation by averaging together those particular sets of pixels. But we can still see that the zeros have a different shape than the ones and the twos and so on. So the differences between the images are still well represented here. So what we did was basically compress from the 64 features in the original data to only 16 features, but because we are clustering the features by similarity, we are minimizing the amount of information that we're losing when we are doing this reduction in dimensionality. Okay, so to sum up, we saw this idea of hierarchical clustering to have clusters of clusters and nested clusters in a hierarchical structure. And for this, we need not only to be able to measure some similarities or differences between examples, but also apply those metrics for comparing clusters. And this is what we call linkage, which is the application of these similarity or dissimilarity measures to comparing clusters. We saw two different approaches to hierarchical clustering, a bottom-up approach in agglomerative clustering, which starts from the bottom. Everything is disconnected in individual clusters, but then we cluster iteratively until we can group them all together or until we reach the desired number of clusters. The top-down approach is a divisive clustering where we start with a single cluster and then keep breaking it down, and bisecting k-means is one possible implementation of that, where we use k-means with k equal to 2 to bisect, to cut into two clusters, each cluster that we are splitting. We saw the effects of different linkage metrics, and we saw also the application of clustering to agglomerating features. Instead of clustering examples, we are clustering features and simplifying the representation of our data in this way. We use the hierarchical clustering in this case because scikit-learn has this agglomerative clustering implementation for features specifically, but in theory you could use any clustering algorithm for this purpose. So if you want to read more, section 7.7 of Alpaiden's book covers the hierarchical clustering, and you have also here in the scikit-learn documentation, you have several examples of clustering, and including these agglomerative clustering algorithms that we saw here.